The universe is a place of unimaginable power, where forces beyond comprehension collide in explosions of raw energy. Picture this: a dying star, billions of times brighter than our sun, detonates in a single cataclysmic instant. For a fleeting moment, it outshines entire galaxies, blasting waves of radiation across the cosmos. This is a supernova, one of the most violent events in existence, and it's just the beginning of the chaos that shapes our universe. These aren't just distant spectacles, they're the engines of creation and destruction, forging the very elements that make up our world and our bodies. Every atom in your hand, every breath you take, was born in the heart of a star's violent death. But supernovas are just the opening act. Beyond them lurk black holes, cosmic vacuum cleaners so powerful they twist space and time itself. Imagine two of these monsters spiraling toward each other, locked in a gravitational dance that ends in a collision so violent it sends ripples through the fabric of reality. These gravitational waves stretch and squeeze the universe, carrying echoes of the explosion across billions of light years. And then there are hypernovas, gamma-ray bursts, and quasars, events so energetic they could sterilize entire galaxies in seconds. The universe isn't just vast and beautiful, it's a battlefield where titanic forces clash in ways that defy human understanding. That's where this journey begins. Over the next 30 facts, we'll dive into the most extreme, mind-bending events the cosmos has to offer. You'll discover how a single burst of gamma rays could wipe out life on Earth from halfway across the universe, how black holes can rip stars apart like tissue paper, and how the biggest explosion since the Big Bang still leaves scars on the sky. This isn't just a list, it's a voyage into the heart of cosmic violence where the laws of physics are pushed to their limits. So buckle up. The universe is about to show you just how terrifyingly magnificent it really is. A supernova is the universe's most spectacular fireworks show, a star's final, furious act of defiance before it collapses or vanishes entirely. When a massive star, at least 8 times heavier than our sun, runs out of fuel, its core can no longer resist the crushing weight of its own gravity. In less than a second, the star implodes, then rebounds in a shockwave so powerful it rips the entire star apart. The explosion unleashes more energy than our sun will produce in 10 billion years, shining brighter than an entire galaxy for weeks. But not all supernovas are created equal. Some, called Type 2, happen when colossal stars, true cosmic giants, exhaust their nuclear fuel and collapse under their own weight. The outer layers slam into the dense core, rebounding in a cataclysmic detonation that leaves behind either a neutron star or a black hole. Others, known as Type 1a, are even more violent. These occur when a dead star called a white dwarf steals material from a companion until it hits a critical mass, triggering a runaway thermonuclear explosion so precise that astronomers use them as cosmic measuring sticks. What makes supernovas truly astonishing isn't just their destructive power, it's what they leave behind. In their fiery death throes, these stars forge the heaviest elements in existence, from the gold in your jewelry to the uranium that powers nuclear reactors. Every ounce of lead, every speck of platinum was forged in the heart of a dying star and scattered across space by these titanic blasts. Without supernovas, the universe would be a much emptier place, just hydrogen, helium, and the faint echoes of the Big Bang. But thanks to these violent cosmic factories, we have planets, oceans, and even the building blocks of life itself. So the next time you look up at the night sky, remember, those silent points of light aren't just distant suns. Some of them are ticking time bombs, ready to unleash unimaginable power. And when they do, they'll seed the cosmos with the very ingredients that make our existence possible. If a supernova is the universe's grand finale, then a hypernova is that same explosion cranked up to 11, a cosmic catastrophe so extreme it redefines violent. When stars 30 times more massive than our sun reach the end of their lives, They don't just collapse, they detonate with such ferocity that the explosion outshines 100 ordinary supernovas combined. This is a hypernova, a rare and monstrous event that doesn't just destroy a star, it tears it apart in a way that sends shockwaves through the fabric of space itself. What sets hypernovas apart isn't just their raw power, it's the deadly afterparty. As the star's core collapses into a black hole, twin jets of plasma shoot outward at nearly the speed of light, piercing through the star's outer layers like cosmic blowtorches. These jets generate gamma-ray bursts, the most luminous flashes of energy in the known universe. In just a few seconds, a single gamma-ray burst can release more energy than our Sun will emit in its entire 10 billion-year lifetime. If one of these beams were to hit Earth, even from thousands of light-years away, it could strip our ozone layer and trigger a mass extinction. But here's the chilling part: we've already witnessed their devastation. In the year 774, Earth was bathed in an intense wave of gamma radiation, likely from a hypernova or neutron star collision. Ancient tree rings from that period show a sudden spike in radioactive carbon, evidence of a near miss. And in 1998, astronomers detected a gamma-ray burst so bright it was briefly visible to the naked eye, despite originating from a galaxy 7.5 billion light-years away. That's halfway across the observable universe. Hypernovas don't just obliterate, they create. The same forces that generate gamma-ray bursts also forge elements heavier than iron, like gold and platinum, flinging them into space at incredible speeds. Without these apocalyptic explosions, the universe would lack the building blocks for rocky planets and life itself. So while hypernovas are terrifying in their destructive potential, they're also cosmic alchemists, turning death into the raw materials for new beginnings. The next time you marvel at a starry sky, remember somewhere out there, a hypernova could be brewing, ready to rewrite the rules of physics in a blinding instant. Gamma-ray bursts are the universe's ultimate death rays, blinding flashes of energy so intense they can outshine 1 million galaxies combined. These cosmic lasers, lasting from milliseconds to several minutes, come in two terrifying varieties. The long bursts, stretching over 2 seconds, are the dying screams of hypergiant stars collapsing into black holes. As the star's core implodes, it fires twin jets of plasma at near light speed, piercing through the stellar corpse like a cosmic blowtorch. What emerges is a beam of gamma radiation so focused and powerful it could sterilize planets thousands of light-years away. Short bursts lasting less than 2 seconds are even more sinister. These originate from neutron star mergers, celestial car crashes where two ultra-dense stellar corpses spiral into each other. When they collide, they create a black hole in a matter of milliseconds, releasing a tsunami of gamma rays and gravitational waves. The Kilonova explosion that follows showers space with heavy elements like gold and platinum, proving even the universe's most violent events can forge beauty from chaos. The sheer scale of these explosions defies comprehension. In 2008, astronomers witnessed a gamma-ray burst so luminous it was briefly visible to the naked eye despite erupting 7.5 billion light-years away. For 30 seconds, this single event outshone every star in our galaxy combined. If a similar burst happened within our cosmic neighborhood, even thousands of light-years away, the radiation could strip Earth's ozone layer and trigger a mass extinction. Evidence suggests this might have happened before ancient ice cores and tree rings reveal radioactive isotopes consistent with a nearby gamma-ray blast around the year 775. Yet these apocalyptic events also shape the cosmos in profound ways. The same processes that generate gamma-ray bursts forge the heaviest elements in existence, scattering them across galaxies to birth new stars and planets. Without these cataclysms, the universe would lack the ingredients for rocky worlds, or life itself. So while gamma-ray bursts are terrifying in their destructive potential, they are also cosmic architects, rewriting the rules of physics with every Earth-shattering detonation. The next time you gaze at the night sky, remember somewhere in the darkness, a star might be moments away from unleashing a beam of energy that could rewrite the fate of entire worlds. Quasars are the universe's ultimate powerhouses, ancient, ravenous beasts lurking in the depths of space, devouring everything in their path. Born in the chaotic early universe, these brilliant beacons are the cores of young galaxies, where supermassive black holes, millions or even billions of times heavier than our Sun, feast on vast clouds of gas and dust. But unlike ordinary black holes that lurk in darkness, quasars transform their destruction into blinding light, becoming the brightest objects in existence. A single quasar can outshine 1,000 galaxies combined, blazing across the cosmos like a cosmic lighthouse visible from billions of light years away. What makes quasars truly terrifying isn't just their hunger, it's the way they unleash their fury. As matter spirals into the black hole's crushing grip, it forms a swirling disk of superheated plasma, glowing white-hot under the strain of unimaginable forces. But the real violence happens at the poles, where magnetic fields twist into colossal jets, catapulting charged particles at nearly the speed of light. These jets stretch for hundreds of thousands of light years, punching through intergalactic space like cosmic flamethrowers, capable of sterilizing entire star systems in their path. The sheer scale of a quasar's energy defies belief. The most luminous ones, like the record-breaking quasar SDSS J0100 plus 28022, shine with the brightness of 600 trillion suns. To put that in perspective, if you placed one at the distance of Pluto, it would vaporize Earth in an instant. Yet these monsters aren't just relics of the past, they're still active today, hidden in the hearts of distant galaxies. Even our own Milky Way once hosted a quasar, its black hole now dormant after consuming most of the nearby fuel. But quasars aren't just destructive, they're also cosmic architects. Their intense radiation and powerful jets can trigger star formation in surrounding gas clouds, building new generations of stars even as they tear others apart. And because their light takes billions of years to reach us, they act as time capsules, offering a glimpse into the universe's violent adolescence. Every quasar we see is a message from the distant past, a reminder that the cosmos was once a far more chaotic and radiant place. So while these celestial monsters may seem like nightmares, they're also key to understanding how galaxies, and even life itself, came to be. Blazars turn the raw terror of quasars into something far more personal because these cosmic monsters are staring straight at us. Imagine a supermassive black hole, billions of times heavier than our Sun, devouring everything in its path while firing twin jets of plasma at nearly the speed of light. Now picture one of those jets aimed directly at Earth, amplifying its brilliance to blinding levels. That's a blazar, a quasar with its deadliest feature pointed right in our direction. What makes blazars so unnerving isn't just their glare, it's what they're hurling at us. Those jets aren't just made of light, they're packed with high-energy particles, cosmic rays that can pierce through planets like bullets through tissue paper. Some of these particles, called neutrinos, are so elusive they pass through entire stars without slowing down. Yet when they collide with atoms deep in Antarctic ice, scientists can detect the faint flashes they leave behind. In 2017, researchers traced one such neutrino back to a blazar 4 billion light-years away, marking the first time we've pinpointed a source for these ghostly particles. But cosmic rays from blazars are even more extreme. These aren't just stray atoms, they're protons and atomic nuclei accelerated to energies 1,000,000 times greater than anything our most powerful particle colliders can produce. When they slam into Earth's atmosphere, they trigger cascades of secondary particles, creating showers of radiation that stretch for miles. The highest energy cosmic rays ever detected carry as much kinetic energy as a fast-pitched baseball, all packed into a single subatomic particle. And many of them likely come from blazars, turning these distant objects into celestial particle accelerators of unimaginable scale. Here's the twist: despite their ferocity, blazars are helping us unravel the universe's secrets. Their jets act like natural laboratories, testing physics under conditions we could never replicate on Earth. By studying how their light flickers and polarizes, astronomers can map the twisted magnetic fields near black holes, regions where gravity bends space into knots. And because their light takes billions of years to reach us, blazars serve as time machines, offering snapshots of the early universe's most violent environments. So while a blazar's gaze might seem like a cosmic death ray, it's also a beacon of discovery. Every pulse of light, every neutrino they send our way carries clues about how black holes feed, how particles reach impossible speeds, and how the universe orchestrates its most extreme events. The next time you look up at the night sky, remember somewhere out there, a blazar might be silently watching, its jet carving a path through the darkness straight toward Earth. Tidal disruption events are the universe's most gruesome form of celestial punishment, a star's death sentence for straying too close to a black hole's lethal grasp. Picture a sun-like star minding its own business in the quiet of space when gravity suddenly yanks it off course. As it plunges toward the black hole, the star's outer layers stretch into a thin, glowing strand of plasma, a process astronomers grimly call spaghettification. The black hole's tidal forces, far stronger on the star's near side than its far side, pull harder than the star's own gravity can resist. The result: a stellar massacre where the star is literally ripped apart atom by atom. But the violence doesn't stop there. The shredded stellar material doesn't just vanish, it spirals into a swirling, superheated disk around the black hole, glowing brighter than a billion suns as it's compressed and heated to millions of degrees. This accretion disk becomes a cosmic beacon, emitting flares of X-rays and ultraviolet light so intense they can outshine entire galaxies for months. In 2011, astronomers witnessed one such event in a galaxy 3.9 billion light-years away, where a black hole weighing millions of solar masses devoured a star half the size of our Sun. The resulting flare burned for over a year, its light echoing across the cosmos like a scream in the dark. What makes these events so fascinating isn't just their brutality, it's what they reveal about black holes themselves. The way a star is torn apart depends on the black hole's size. Smaller black holes with their sharper gravitational gradients can shred stars before they even cross the event horizon. Supermassive ones, like the beast at the center of our Milky Way, might swallow smaller stars whole with barely a burp. And sometimes, if the star is massive enough, its core can survive the initial encounter only to be flung back into space as a hypervelocity wreck, doomed to wander the galaxy alone. These cataclysms are more than just cosmic spectacles. They're vital clues to understanding how black holes grow and how they shape their galaxies. The metals forged in the star's death throes are scattered into space, seeding future generations of stars and planets. And by studying the light from these flares, astronomers can map the black hole's surroundings with unprecedented detail, probing regions where gravity warps space into knots. So while tidal disruption events might seem like freak accidents, they're actually part of the universe's grand recycling program, turning the death of one star into the birth of something new. The next time you look up at the night sky, remember somewhere out there, a star might be meeting its end in the jaws of a black hole, its final moments lighting up the cosmos in a blaze of glory. And in that violent death, the universe is quietly writing the next chapter of its endless story. Rogue black holes are the universe's most elusive predators, cosmic phantoms drifting through the void, invisible and untrackable until they strike. Unlike their stationary cousins anchored at the centers of galaxies, these lone wanderers are born from chaos, ejected into the darkness during violent galactic collisions. When two galaxies merge, their central black holes spiral toward each other, locked in a gravitational dance. If the conditions are just right, the final collision can kick one of them outward at staggering speeds, hurling it into intergalactic space like a bullet fired from a cosmic gun. One such rogue was discovered in 2017, lurking just 8,000 light-years from Earth, close enough, in astronomical terms, to raise eyebrows. Astronomers noticed subtle deflections in the motion of nearby stars, their paths bending as if tugged by an unseen hand. The culprit, a black hole roughly 7 times the mass of our Sun, drifting silently through the Milky Way's halo. Unlike active black holes that announce their presence with glowing accretion disks, this one was dark, detectable only by its gravitational fingerprint on the surrounding stars. The terrifying beauty of rogue black holes lies in their stealth. Without the telltale glow of infalling matter, they're nearly impossible to spot unless they pass directly between us and a distant star, bending its light like a lens. Even then, the effect is fleeting, a momentary flicker in the data. Some researchers estimate there could be millions of these nomads hiding in our galaxy alone, their paths weaving silently between the stars. And if one were to drift too close to our solar system, its gravity could fling planets from their orbits or dismantle the delicate balance that makes life on Earth possible. Yet these dark wanderers also tell a deeper story. Their existence confirms some of the most dramatic predictions of Einstein's theory of relativity, particularly how black holes can recoil from mergers, carrying the scars of their violent births across the cosmos. By studying their trajectories, astronomers can reconstruct the Milky Way's turbulent history, tracing the ancient collisions that shaped our galactic neighborhood. So while rogue black holes might sound like the stuff of nightmares, they're also cosmic archaeologists preserving clues about the universe's most violent encounters. The next time you gaze up at the night sky, consider this. Somewhere in that vast darkness, a rogue black hole could be gliding past, unseen and undetected. It's a reminder that even in the quietest corners of space, the universe harbors forces beyond our sight and beyond our imagination. Neutron star collisions are the universe's ultimate heavy metal factories, cosmic smash-ups so violent they forge gold, platinum, and other precious elements in the blink of an eye. Picture 2 city-sized stellar corpses, each so dense a single teaspoon would weigh 1 billion tons, locked in a death spiral. As they circle each other hundreds of times per second, their immense gravity distorts space itself, sending out ripples called gravitational waves. Then, in a final cataclysmic embrace, they collide, triggering an explosion brighter than 1 million suns, a kilonova. This isn't just a light show, it's the universe's way of minting the heaviest elements in existence. The historic detection of one such collision in 2017 changed astronomy forever. For the first time, scientists captured both gravitational waves and light from the same event, a neutron-star merger 130 million light-years away. The gravitational wave observatories LIGO and Virgo felt the spacetime ripples, while telescopes across the globe spotted the resulting Kilonova, a fiery cloud glowing with the unmistakable signature of newly forged gold, platinum, and uranium. Within days, astronomers calculated that this single event produced over 10 times Earth's mass in gold alone, flinging it into space at 1/3 the speed of light. What makes these collisions so extraordinary isn't just their destructive power, it's their creative potential. In the chaos of the merger, neutron-rich material is flung outward, forming an ultra-hot soup where atomic nuclei capture neutrons at breakneck speed. This rapid process, called the R process, builds heavy elements atom by atom, creating everything from the iodine in your body to the uranium that powers nuclear reactors. Without neutron star collisions, the periodic table would stop at iron, leaving the universe devoid of the building blocks for planets, life, and even the jewelry we wear. But the real shocker, these events are far more common than we once thought. Before 2017, many assumed neutron star mergers were rare. Now, thanks to advanced detectors, we know they might happen as often as once every 10,000 years per galaxy. That means the Milky Way's treasure trove of gold and platinum likely came from thousands of these ancient cosmic crashes. Even more astonishing, some of the gold in your wedding ring or smartphone might have been forged in a neutron star collision that occurred billions of years before our solar system was born. The Kilonova's aftermath is just as mesmerizing. The explosion creates a swirling debris field laced with radioactive elements, glowing blue from the heat of nuclear decay before fading to red as it expands. This celestial alchemy leaves behind either a hyper-dense neutron star or, if the combined mass is too great, a newborn black hole, a grim reminder that even in creation, destruction is never far away. So the next time you hold a piece of gold, remember, its journey began in one of the most violent events imaginable, a stellar collision so powerful it warped the fabric of space and time. These cosmic smash-ups aren't just spectacles, they're the universe's way of recycling death into new life, proving that even in the darkest corners of space, beauty can emerge from chaos. Magnetars are the universe's ultimate cosmic electromagnet. It's neutron stars so magnetically charged they redefine the word extreme. Imagine a stellar corpse no bigger than Manhattan, yet packing the mass of two suns, spinning furiously while wrapped in a magnetic field a quadrillion times stronger than Earth. That's a magnetar, a celestial powerhouse where physics textbooks get rewritten daily. These objects are so dense that just a teaspoon of their material would weigh 1 billion tons, and their magnetic fields are so intense they could strip the data from every credit card on Earth from halfway across the Milky Way. But what truly sets magnetars apart isn't just their strength, it's their temper. Unlike quiet neutron stars, magnetars regularly unleash terrifying flares called starquakes, where their crust, a hyper-dense lattice of iron nuclei, suddenly cracks under the strain of twisted magnetic fields. The energy released in these explosions is mind-blowing. In December 2004, a magnetar 50,000 light-years away in the constellation Sagittarius erupted with a flare so powerful it briefly ionized Earth's upper atmosphere, even though the blast originated halfway across our galaxy. For a fraction of a second, it outshone the full moon in gamma rays despite being buried behind thick clouds of interstellar dust. The mechanics behind these eruptions are even wilder. A magnetar's magnetic field isn't just strong, it's knotted like a rubber band twisted too tightly. When the stress becomes too much, the crust snaps, releasing pent-up energy in a burst of X-rays and gamma rays. These starquakes can release more energy in 1/10 of a second than our sun emits in 100,000 years. And sometimes the outbursts come with a deadly bonus: relativistic fireballs, jets of charged particles accelerated to near light speed, capable of sterilizing any planetary system unlucky enough to lie in their path. Yet magnetars aren't just agents of destruction. Their extreme environments serve as natural laboratories for testing physics under conditions impossible to replicate on Earth. The way their magnetic fields warp space-time, for example, could help us probe the secrets of quantum gravity, and their flares act as cosmic lighthouses, illuminating the interstellar medium in ways that reveal hidden gas clouds and magnetic fields. Even more astonishing, some scientists speculate that magnetars could be the engines behind mysterious fast radio bursts, those fleeting, ultra-powerful radio signals that have puzzled astronomers for years. The scariest part, magnetars are more common than we once thought. Astronomers estimate there could be tens of millions lurking in our galaxy alone, remnants of massive stars that burned out in spectacular fashion. And while the nearest known magnetar is still thousands of light-years away, a close encounter with one of these magnetic monsters could spell doom for life on Earth. A flare from just a few light-years away could strip our ozone layer, bathe the planet in lethal radiation, and trigger a mass extinction. But here's the twist: without magnetars, the universe might lack some of its most dramatic phenomena. Their eruptions seed space with high-energy particles, influencing star formation and galactic chemistry. And their very existence pushes the limits of what we thought possible, reminding us that the cosmos is far stranger and far more violent than we ever imagined. So the next time you feel a magnetic pull toward the unknown, remember somewhere out there, a magnetar is lurking, its colossal magnetic field coiled like a spring, ready to unleash chaos on a galactic scale. Active galactic nuclei are the universe's ultimate cosmic furnaces, supermassive black holes turned into engines of unimaginable power, devouring stars and gas with such ferocity they can reshape entire galaxies. At the heart of nearly every large galaxy, including our own Milky Way, lurks one of these gravitational monsters, weighing millions or even billions of times more than our Sun. But unlike dormant black holes like Sagittarius, a star which sits quietly at our galaxy's center, active galactic nuclei are anything but calm. When these behemoths feed, they transform their meals into blinding radiation, outshining every star in their host galaxy combined. The process begins when gas, dust, or even entire stars spiral too close to the black hole's event horizon. As this material falls inward, friction heats it to millions of degrees, creating a swirling accretion disk that glows with the energy of 1 trillion suns. But the real spectacle happens above and below the disk, where magnetic fields twist into colossal jets, launching particles at nearly the speed of light. These jets can stretch for hundreds of thousands of light years, carving through interstellar space like cosmic blowtorches. In some cases, they're so powerful they can blow gas clear out of the galaxy, starving it of the material needed to form new stars. Our own Milky Way wasn't always the peaceful spiral we see today. Sagittarius, a star, though now dormant, shows signs of a violent past. Ancient light echoes in nearby gas clouds reveal that roughly 3.5 million years ago it erupted in a titanic explosion. A safet flare so bright it would have been visible from neighboring galaxies. The blast scorched the Magellanic Stream, a river of gas trailing our galactic companions, with enough energy to light up the night sky for our distant ancestors. And there's evidence of even earlier outbursts, suggesting our black hole wakes from its slumber every few million years to reshape its surroundings. What makes active galactic nuclei so fascinating isn't just their destructive potential, it's their role as cosmic regulators. By heating surrounding gas or blasting it away entirely, they can stifle star formation, effectively putting a galaxy's growth on pause. In some cases, they might even trigger it as shockwaves compress nearby gas clouds into new stellar nurseries. These black holes don't just consume, they control, acting as gravitational thermostats that maintain a delicate balance between chaos and order. Without them, galaxies might burn through their fuel too quickly, leaving the universe dark and lifeless long before planets or life could emerge. Yet for all their power, active galactic nuclei are fleeting. Their brilliant outbursts last only as long as there's fuel to feed them, a cosmic blink lasting perhaps 100 million years. That's why we see them mostly in the distant universe, their light taking billions of years to reach us. Each one is a snapshot of a galaxy's turbulent youth, a reminder that even the mightiest structures in the cosmos are shaped by the appetites of the monsters at their cores. So while Sagittarius, a star, sleeps today, its past eruptions and the possibility of future ones hint that our quiet corner of the universe was once as violent as any other. And somewhere out there, another galaxy's heart is waking up, ready to unleash a storm of light that will echo across the cosmos. Galactic collisions are the universe's most spectacular demolition derbies, cosmic pileups where entire galaxies, each home to hundreds of billions of stars, smash together in a slow-motion train wreck that lasts millions of years. Picture this, the Andromeda Galaxy, a spiral beauty twice the size of our Milky Way, hurtling toward us at 250,000 miles per hour. In about 4 billion years, it'll plow straight into our galactic neighborhood, twisting spiral arms into chaotic ribbons of gas and dust, and flinging stars into the void like sparks from a grinding wheel. This isn't science fiction, it's an inevitable fact written in the language of gravity, and the aftermath will rewrite the night sky forever. But the real violence of galactic mergers isn't in the stars themselves, it's in the chaos they unleash. As galaxies collide, their gas clouds slam together, compressing under unimaginable pressure until they ignite in furious bursts of star formation. These starburst regions, like the antennae galaxy's fiery core, become cosmic nurseries on steroids, churning out new stars 100 times faster than a normal galaxy. The most massive of these stars burn bright and die young, exploding as supernovas that seed space with heavier elements while their shockwaves trigger even more star birth. It's a chain reaction of creation and destruction where violence fuels new life. At the heart of this maelstrom, something even more terrifying awakens: supermassive black holes. Normally dormant, these monsters stir as the galaxies merge, gorging on the torrents of gas and stars funneled toward them by the collision. As they feed, their accretion disks glow with the heat of 1 trillion suns, transforming into quasars, beacons so bright they outshine everything else in the universe. The black holes themselves begin a deadly dance, spiraling closer until they either merge in a gravitational wave, blast, or fling one another away like cosmic slingshots. The Milky Way and Andromeda won't just collide once, they'll pass through each other multiple times, their gravity weaving them into a single, elliptical galaxy over billions of years. Stars will be tossed into wild new orbits, and our solar system might find itself flung far from the galactic core, adrift in a sea of alien suns. Yet amid the chaos, there's a strange beauty. These collisions are how galaxies grow, recycle their gas, and ignite new generations of stars. Without them, the universe would be a static graveyard of isolated islands, never evolving into the vibrant cosmic web we see today. So while the idea of galaxies crashing sounds apocalyptic, it's also the universe's way of reinventing itself. Every giant elliptical galaxy we see, every quasar lighting up the early cosmos, is evidence of these titanic mergers, proof that destruction and creation are two sides of the same coin. And when Andromeda finally arrives, it won't just be an ending. It'll be the beginning of something new, a brighter, more monstrous galaxy forged in the fires of cosmic violence. Dark matter annihilation could be the universe's most elusive light show, a silent fireworks display where invisible particles collide and vanish in bursts of gamma rays. Imagine two dark matter particles, each a ghostly fragment of the cosmos that neither emits nor reflects light, locked in a deadly dance. If they meet with just the right conditions, they might annihilate each other completely, transforming their mysterious mass into pure energy. The result, a flash of gamma radiation, the universe's brightest and most energetic light. These explosions could be happening right now in the densest regions of space: galactic cores, dwarf galaxies, or vast halos where dark matter clumps like unseen fog. Scientists call this process annihilation, and it's one of the few ways we might finally detect dark matter directly. The Fermi Gamma Ray Space Telescope, orbiting Earth since 2008, has spent years scanning the skies for these telltale gamma ray signatures. It's hunting for excess radiation in places like the center of our Milky Way, where dark matter is thought to pool in staggering quantities. The data reveals faint but tantalizing hints, an unexplained glow of gamma rays that just might be the smoking gun of dark matter's hidden interactions. Some researchers believe these signals could come from weakly interacting massive particles, or WIMP, hypothetical dark matter particles that annihilate when they collide. But the search isn't simple. Gamma rays come from countless violent sources: pulsars, supernova remnants, even distant quasars. Teasing apart a potential dark matter signal from this cosmic noise is like listening for a whisper in a hurricane. The Fermi team has to meticulously rule out every other possibility, analyzing the energy spectrum of these gamma rays for the precise fingerprint that annihilation would leave behind. It's detective work on a galactic scale where even the slightest anomaly could rewrite our understanding of the universe. The implications are staggering. If confirmed, dark matter annihilation wouldn't just solve one of cosmology's greatest mysteries, it would reveal a hidden layer of particle physics beyond the standard model. These collisions could produce exotic particles we've never seen, or even hint at extra dimensions curled up in the fabric of space. And because dark matter outweighs normal matter 5 to 1, its annihilation could be shaping the cosmos in ways we're only beginning to imagine, heating gas in early galaxies or seeding the universe with high-energy radiation. Yet for all its potential, dark matter annihilation remains just out of reach, a shadowy puzzle with pieces that refuse to fit. Some theories suggest the signals Fermi detected might come from something else entirely, like undiscovered pulsars or turbulent magnetic fields. Others argue we might need even more sensitive instruments to catch dark matter in the act. But one thing's certain, every flicker of unexplained gamma rays brings us closer to unraveling the universe's darkest secret. So while we can't see dark matter directly, its explosive farewell might finally shine a light on the invisible architecture of reality itself. Vacuum decay isn't just science fiction, it's the universe's ultimate reset button, a hypothetical catastrophe so absolute it could erase existence in the blink of an eye. Picture an infinitesimally small bubble somewhere in the vastness of space, where the very fabric of reality flickers into a lower energy state, a true vacuum. This bubble wouldn't just sit there, it would expand at the speed of light, rewriting the laws of physics as it goes, turning everything in its path into something unrecognizable. Stars, galaxies, even the atoms in your body would cease to function as they once did, not with a bang, but with a silent, unstoppable reconfiguration of the cosmos itself. What makes this scenario so chilling is the physics behind it. Our universe might exist in what scientists call a false vacuum, a stable but not perfectly stable state, like a marble resting in a shallow dip on a hillside. It seems solid, but given the right nudge, it could roll into a deeper valley, releasing energy as it goes. In quantum terms, that nudge could happen spontaneously anywhere, anytime, thanks to random fluctuations. The resulting bubble of true vacuum would have fundamentally different physical constants. The forces that hold atoms together, the speed of light, even the nature of time could change instantly within its boundary. And because it expands at light speed, there'd be no warning, no chance to escape, just an invisible wall of annihilation rewriting reality as it passes. The most unsettling part, we might already be in the danger zone. Some theories suggest the Higgs field, the quantum entity that gives particles mass, could be the trigger. If its current state isn't the lowest possible energy level, a single quantum event could tip it over the edge. Research at particle colliders like the Large Hadron Collider has searched for clues, measuring the Higgs boson's mass to assess this risk. So far, the numbers suggest our vacuum is probably stable, but probably isn't the same as definitely. There's still a slim chance the universe is sitting on a cosmological time bomb, waiting for a random fluctuation to set it off. Yet vacuum decay isn't just a doomsday scenario. It's a window into the deepest mysteries of existence. If it happened, it would prove that our universe's laws aren't set in stone, but are instead just one possible configuration in a multiverse of realities. Some physicists even speculate that this might have already occurred elsewhere, with other regions of space having entirely different physics beyond our cosmic horizon. In a strange way, the possibility of vacuum decay hints that our universe might be far more fragile and far more exotic than we ever imagined. While the odds are astronomically low, likely less than 1 in a trillion over billions of years, the sheer scale of the consequence makes it unforgettable. It forces us to confront the fact that the universe doesn't owe us stability. The rules we take for granted could, in theory, change in an instant. So the next time you look up at the night sky, consider this. The quiet, predictable cosmos we see might just be a temporary arrangement, one quantum fluctuation away from becoming something entirely alien. And in that humbling thought lies one of science's greatest lessons, that even the most fundamental truths of existence might be more fragile than they appear. The Big Bang wasn't just a gentle beginning. It was a firestorm of expansion so violent it makes every supernova look like a candle flicker. In the first trillionth of a second after creation, the universe didn't just grow. It exploded outward at speeds that defy logic, inflating from smaller than an atom to the size of a grapefruit in less time than it takes light to cross a single proton. This was cosmic inflation, a runaway stretch of spacetime so extreme it left permanent scars on the fabric of reality itself. What fueled this frantic expansion? A mysterious form of energy baked into empty space, driving the universe apart faster than light could keep up. As space stretched, quantum fluctuations, tiny ripples in the newborn cosmos got yanked to astronomical sizes. Those microscopic wrinkles became the seeds of all future structure. The denser patches would later pull in matter to form galaxies, while the emptier regions became the vast cosmic voids we see today. Without inflation's brutal stretching, the universe would be a smooth, featureless soup. No stars, no planets, just endless uniformity. The evidence for this violent birth is etched into the oldest light we can see, the cosmic microwave background. This afterglow from the Big Bang shows temperature variations matching inflation's predictions almost perfectly. Ripples in spacetime left by inflation also appear as gravitational waves, faint echoes of the universe's first moments. In 2014, the BICEP 2 telescope team thought they'd spotted these waves, though dust interference later muddied the results. The hunt continues because confirming inflation would mean we're glimpsing physics at energies a trillion times beyond what any particle collider could ever reach. Yet inflation's violence raises even wilder possibilities. Some theories suggest our universe might be just one bubble among countless others in an eternally inflating multiverse, where new universes pop into existence like bubbles in boiling water. Each would have its own laws of physics, its own version of reality, some stillborn, others thriving. If true, it means the Big Bang wasn't a one-time event, but part of an endless cycle of creation more extravagant than anything we've dared imagine. The legacy of inflation is all around us in every galaxy, every star, every atom. The same forces that nearly tore space-time apart also set the stage for everything that followed. So when you look up at the night sky, you're seeing the aftermath of the most violent growth spurt in history, a moment when the universe rewrote the rules of existence faster than the speed of thought. And somewhere out there, beyond the edge of our vision, inflation might still be happening, birthing new universes in explosions of energy that make the Big Bang look like a whisper. Primordial black holes might be the universe's oldest ticking time bombs, tiny, ancient relics forged in the chaos of the Big Bang itself. Unlike the monstrous black holes formed from dying stars, these hypothetical objects could be as small as an atom yet pack the mass of a mountain, remnants of a time when the newborn universe was a seething, dense soup of unimaginable pressure. If they exist, they'd be lurking unseen throughout the cosmos, drifting through galaxies like invisible ghosts. But here's the twist: their tiny size doesn't make them harmless. Thanks to Hawking radiation, these black holes could be slowly evaporating, and their final moments might unleash explosions brighter than a supernova. The idea comes from Stephen Hawking's revolutionary theory. Black holes aren't entirely black. They emit particles, losing energy and mass over time. For giant black holes, this process is achingly slow, taking longer than the current age of the universe to even make a dent. But primordial black holes, if they're small enough, could be evaporating right now, their final moments marked by a catastrophic burst of gamma rays. Imagine a black hole the size of a proton, left over from the Big Bang, finally sputtering out of existence in a flash of energy equivalent to millions of atomic bombs. These bursts would be fleeting but insanely powerful, potentially detectable across the universe as brief, inexplicable blips of radiation. The hunt for these explosions is already underway. Telescopes scanning the sky for gamma-ray bursts occasionally catch mysterious, ultra-short flashes that don't fit the usual patterns of neutron star collisions or supernovas. Some researchers suspect these could be the dying screams of primordial black holes, their hawking radiation flares acting as cosmic death certificates. If confirmed, the discovery would reshape our understanding of black holes, dark matter, and even the Big Bang itself, because primordial black holes might be far more than relics. Some theories suggest they could account for at least part of the universe's missing dark matter, silently influencing galaxies while remaining utterly invisible. Yet their existence remains one of cosmology's most tantalizing mysteries. The conditions needed to create them in the early universe are extreme fluctuations in density so intense they collapse directly into black holes rather than forming stars or galaxies. If they're out there, they'd be the ultimate survivors, persisting for nearly 14 billion years only to vanish in a final, spectacular act of violence. Their explosions wouldn't just be a curiosity, they'd be a window into the universe's most extreme physics, testing Hawking's predictions under conditions no lab could ever replicate. So while we haven't found definitive proof of primordial black holes yet, the search itself is a reminder of just how strange the cosmos can be. Even the tiniest objects left over from creation could rewrite the rules of reality, proving that sometimes the most violent events come in the smallest packages. And if one of them detonates nearby, even for a fraction of a second, it might finally reveal a hidden chapter in the universe's earliest moments. The sun might seem like a steady, reliable presence, but don't be fooled. Lurking beneath its calm surface is the potential for a catastrophe that could bring modern civilization to its knees. Solar superflares are cosmic tantrums, eruptions of energy so powerful they make ordinary solar flares look like firecrackers. In 1859, Earth was hit by the Carrington event, a solar storm so intense it set telegraph lines on fire and made the northern lights visible as far south as Cuba. But that was nothing compared to what the sun is truly capable of. Astronomers have spotted younger, sun-like stars unleashing superflares 100 times stronger, and there's no reason our sun couldn't do the same. These superflares don't just fry satellites, they threaten the very backbone of modern life. A strike as powerful as those seen on other stars would send a tsunami of charged particles crashing into Earth's magnetic field, inducing currents strong enough to melt power transformers and knock out grids for months or even years. Imagine waking up to a world without refrigeration, fuel pumps, or cell service hospitals running on backup generators until those too run dry. The global economic fallout could reach trillions of dollars, setting technology back decades. And unlike hurricanes or earthquakes, this disaster wouldn't be localized. It would strike the entire planet at once. What makes superflares so terrifying is their unpredictability. The sun cycles through periods of high and low activity every 11 years, but a superflare could strike at any time with little warning. NASA Kepler telescope has observed distant stars erupting without rhyme or reason, some blasting out energy equivalent to 1 billion atomic bombs in minutes. If our sun followed suit, we'd have roughly 18 hours between the flare's eruption and its impact, barely enough time to shut down vulnerable grids before the storm hits. Yet there's a strange silver lining. Studying these violent outbursts on other stars has given scientists new tools to predict and possibly mitigate their effects. By analyzing the light patterns of superflares, astronomers can identify warning signs that might precede an eruption. Spacecraft like the Parker Solar Probe are diving perilously close to the sun's corona, gathering data on the magnetic tangles that fuel these explosions. And engineers are hardening power grids with surge protectors designed to absorb the worst of a solar storm's fury. The irony is hard to miss. The same star that gives us warmth and light could also plunge us into darkness. But understanding its darker potential might be the key to surviving it. So the next time you feel the sun's rays on your skin, remember, it's not just a life giver. It's a sleeping giant, one with the power to rewrite human history in a single, violent flash. The universe's final act might be the most violent encore of all, a choice between two cosmic doomsdays so extreme they make black holes look tame. On one side, there's the Big Crunch, a scenario where gravity finally wins its billion-year tug of war with expansion. Imagine every galaxy reversing course, hurtling back toward each other in a nightmarish rewind of the Big Bang. Space itself would heat up as galaxies merge, stars collide, and black holes feast on the wreckage. In the final moments, all matter, every atom, every photon, would be crushed into a singularity hotter and denser than anything since creation. It wouldn't just be an ending, it'd be the universe folding in on itself like a house of cards in a hurricane. Now flip the script to the Big Rip, where dark energy, the mysterious force accelerating the universe's expansion, goes rogue. Instead of a slow fade, the cosmos tears itself apart in a crescendo of violence. First, galaxies would be ripped from each other, then stars from their galaxies. Planets would disintegrate as the force overwhelms gravity, and finally, atoms themselves would be shredded into particles that can never reunite. The universe wouldn't just end, it would dissolve into a cold, lonely mist of fundamental particles, each forever out of reach of the others. Recent measurements of dark energy make this second scenario alarmingly plausible. Observations of distant supernovas and the cosmic microwave background suggest dark energy isn't just constant, it might be growing stronger over time. If this phantom energy accelerates, it could reach infinite strength in a finite future, triggering the Big Rip as early as 22 billion years from now. The numbers are staggering. One moment, the Milky Way would still hang intact in the sky. The next, its stars would vanish like sandcastles in a tsunami. Yet the Big Crunch hasn't been ruled out entirely. If dark energy weakens or gravity gains the upper hand, the universe's expansion could slow, halt, and reverse. Some string theorists even propose a cyclical universe, where each Big Crunch births a new Big Bang in an endless loop of destruction and rebirth. It's a poetic idea, but one that hinges on physics we've yet to prove, like higher dimensions or quantum gravity. What's chilling isn't just the scale of these endings, it's how little control we have over them. The fate of the cosmos hangs on dark energy's whims, and we're just passengers on this ride. Whether it's a fiery collapse or a frozen disintegration, the universe's finale will be the ultimate display of its power, a reminder that even the grandest structures are temporary. So while these scenarios might seem impossibly distant, they force us to confront a humbling truth. Everything, from the smallest atom to the largest galaxy, is just borrowing time before the cosmos claims it back. 66 million years ago, Earth experienced a cosmic punch that rewrote the history of life, the Chicxulub impactor, a 6-mile-wide asteroid that struck with the force of 100 million megatons of TNT. To put that in perspective, it released more energy in 1 second than all the world's nuclear arsenals combined. The blast triggered wildfires stretching continents, tsunamis towering hundreds of feet, and a lingering nuclear winter that blocked sunlight for years. But what makes this disaster truly humbling isn't just its scale. It's the fact that in the grand scheme of cosmic violence, it was remarkably small. The universe delivers far worse on a regular basis. Gamma-ray bursts, hypernovas, and quasar jets wield energies billions of times greater, capable of sterilizing entire galaxies. Even within our own solar system, Chicxulub was far from unique. The Moon's cratered surface tells the story of a chaotic past where impacts like these were routine. Jupiter, acting as our cosmic shield, takes hits the size of Earth killers every few decades, like the 1994 Shoemaker-Levy 9 collision, which left scars larger than our planet. Yet Chicxulub's legacy isn't just about destruction, it's a warning. Near-Earth objects half its size could still unleash global catastrophe. Take Apophis, an asteroid once thought to threaten Earth in 2029. Though now deemed safe, its 300-meter width packs enough punch to flatten a country. NASA tracks over 25,000 such objects, with hundreds labeled potentially hazardous. The Tunguska event of 1908, a mere 40-meter rock exploding over Siberia, leveled 800 square miles of forest. Had it hit a city, the toll would have been unimaginable. The real terror lies in what we haven't found. Current surveys miss most asteroids under 140 meters, enough to devastate a continent if they struck. And while Chicxulub-scale impacts are rare, occurring every 100 million years or so, the smaller ones strike far more often. A city killer could arrive with little warning, as nearly happened in 2019 when a 100-meter asteroid dubbed 2019 OK slipped past our telescopes, detected just days before it whistled by at 1/5 the Moon's distance. But here's the twist: Chicxulub's violence also paved the way for our existence. By wiping out the dinosaurs, it cleared the stage for mammals and eventually humans. In a cruel irony, the same cosmic chaos that extinguishes life also reshapes it, proving that even the universe's most brutal acts can birth new beginnings. So while we scan the skies for threats, we're also hunting clues to our own origins, written in the scars of asteroids past. The next Chicxulub is out there, and whether it brings an end or another chance depends entirely on our ability to see it coming. Pulsars are the universe's ultimate cosmic power plants, spinning neutron stars so dense they pack the mass of a sun into a city-sized sphere, all while whirling at dizzying speeds. These stellar corpses don't just sit quietly, they fire beams of radiation from their magnetic poles like interstellar searchlights, sweeping across space with metronomic precision. Each rotation, some faster than a kitchen blender, sends a pulse of energy our way, earning them the nickname cosmic lighthouses. But don't let the steady rhythm fool you. Some pulsars are anything but gentle beacons, they're celestial predators, using those beams to blast apart anything foolish enough to venture too close. Take the Black Widow pulsar, a stellar vampire lurking in our galaxy. This nightmare spins 700 times per second, its beams of gamma rays and charged particles carving through space like a cosmic scythe. Its companion star, once a healthy sun-like object, is now being slowly vaporized by the pulsar's relentless fury. The Black Widow's radiation barrage strips away layers of stellar material atom by atom, creating a glowing cloud of plasma that spirals into oblivion. Over millions of years, this process will leave nothing behind, just the pulsar spinning alone in the darkness, having consumed its partner entirely. What makes pulsar jets so astonishing isn't just their destructive power, it's the physics behind them. The beams aren't just light, they're streams of electrons and protons accelerated to nearly the speed of light, making them the most potent natural particle accelerators in existence. The energy in these jets is so intense it can create antimatter on contact with interstellar gas, a phenomenon we've detected as bursts of positrons, the antimatter twins of electrons. Some pulsars, like the famous Crab pulsar, even power entire nebulas with their radiation, illuminating vast clouds of gas like a cosmic spotlight. Yet for all their ferocity, pulsars are also precision instruments. Their clock-like pulses help astronomers map the galaxy, test Einstein's theory of relativity, and even search for gravitational waves. The millisecond pulsars, spinning hundreds of times per second, keep time more accurately than atomic clocks on Earth. But this precision comes at a price. The magnetic fields around pulsars are trillions of times stronger than Earth's, twisting space-time itself into knots. Any spacecraft venturing near one would be torn apart atom by atom, its navigation systems fried by the relentless barrage of radiation. The Black Widow is just one example of a broader cosmic horror story. Dozens of similar spider pulsars have been discovered, each named after arachnids known for devouring their mates. Some, like the redback pulsar, trap their companions in such tight orbits that the stars deform into teardrop shapes, their outer layers boiling away under the pulsar's glare. Others fling their victims into deep space at escape velocity, leaving behind nothing but a trail of ionized gas. These celestial predators prove that even in death, stars can wield unimaginable power. Power that reshapes worlds, forges elements, and writes the next chapter in the universe's violent history. So the next time you hear the steady tick of a pulsar's signal, remember, what sounds like a cosmic metronome is actually the heartbeat of a monster, one capable of turning solar systems into graveyards with a single sweep of its beam. And somewhere out there, another black widow might be spinning up, ready to claim its next victim. The eerie silence of the cosmos might be the universe's loudest warning, a clue that something is systematically wiping out intelligent life before it can spread among the stars. This chilling idea lies at the heart of the Fermi paradox, the unsettling contradiction between the high probability of alien civilizations existing and our complete lack of evidence for them. One terrifying solution: cosmic violence might be the universe's ultimate exterminator, a series of catastrophic events so frequent and devastating that they act as a great filter, silently culling civilizations before they ever get the chance to say hello. Consider the numbers. Our Milky Way alone contains hundreds of billions of stars, many with Earth-like planets in habitable zones. Statistically, the galaxy should be teeming with life. Yet after decades of listening, we've heard nothing but static. The Great Filter hypothesis suggests there's some insurmountable barrier preventing life from progressing to interstellar communication, and gamma-ray bursts could be prime suspects. These death beams, capable of sterilizing entire star systems, might sweep through galaxies like cosmic scythes, resetting the clock on evolution every few million years. Evidence from Earth's past supports this grim possibility. Tree rings and ice cores show signs of gamma radiation spikes around 775 AD, likely from a nearby stellar explosion. Had it been closer, it could have stripped our ozone layer and triggered a mass extinction. But gamma-ray bursts aren't the only candidates. Hypernovas, those supercharged stellar explosions, could bathe entire galactic neighborhoods in lethal radiation. Or consider quasars, whose jets can cook planets thousands of light years away with high-energy particles. Even our own solar system isn't safe. Rogue black holes or wandering stars could perturb comets into deadly cascades, as may have happened during the late heavy bombardment 4 billion years ago. Each of these events could represent a different filter in a cosmic obstacle course, winnowing down the number of species that make it to technological maturity. The sobering implication: if the Great Filter lies ahead of us rather than behind, if these extinction-level events are inevitable rather than survivable, humanity's window for survival might be terrifyingly narrow. We've already dodged several bullets: the Chicxulub asteroid, the Toba supervolcano, and those mysterious gamma-ray bursts in Earth's history. But what if the universe is rigged against civilizations lasting long enough to become interstellar? The same cosmic violence that forged the elements in our bodies might also be the force that keeps the universe forever silent, a cruel irony written into the fabric of reality itself. Yet there's a strange comfort in this bleak scenario. If cosmic cataclysms are indeed the Great Filter, our very existence becomes extraordinary. We're the outliers, the unlikely survivors of a universe that seems hell-bent on preventing exactly what we're attempting: reaching out into the stars. Every second we continue to exist, we're beating astronomical odds, proving that against all cosmic violence, life can still cling to existence. The silence around us might be terrifying, but it makes every transmission we send, every telescope we build, an act of defiance, a refusal to let the universe have the last word. The sun may seem eternal from our human perspective, but its death has already been written in the laws of physics, a slow-motion apocalypse that will rewrite the solar system. In about 5 billion years, our once stable star will exhaust its hydrogen fuel, triggering a chain reaction that turns it into a monstrous red giant. As the core contracts, the outer layers will expand outward, swallowing Mercury and Venus whole and licking at Earth's orbit with tongues of plasma 10,000 degrees hot. Our planet won't be engulfed immediately, but it will become a lifeless cinder long before that final moment. The oceans boiled away, the atmosphere stripped by solar winds, the crust melted into magma under the unbearable glare of a sun that now fills half the sky. This transformation won't be explosive like a supernova, but in its own way, it's just as violent. The red giant phase represents a star's last desperate attempt to survive, fusing heavier elements in shells around its core while shedding mass in turbulent stellar winds. These winds will carry away nearly half the sun's substance, creating a glowing nebula that will linger for tens of thousands of years, a funeral shroud woven from the star's own dying breaths. Meanwhile, the core will continue collapsing under its own weight, eventually becoming a white dwarf, a diamond-like ember no larger than Earth but so dense that a teaspoon of its material would weigh as much as an elephant. What makes our sun's fate unique is its mediocrity. Stars 8 times more massive meet far more spectacular ends, their cores collapsing into neutron stars or black holes in supernova explosions that outshine entire galaxies. But these violent deaths are also creative forces, forging heavy elements and scattering them across space to birth new stars and planets. Our sun, by contrast, will fade quietly, its white dwarf remnant cooling over trillions of years into a black dwarf, a cold, dark relic of a once brilliant star. The irony is profound. The same gentle stability that allowed life to flourish on Earth also dooms the sun to a comparatively uneventful death. There will be no dazzling supernova, no exotic stellar remnant, just a gradual dimming that leaves the inner solar system unrecognizable. Yet even this slow-motion catastrophe holds a lesson about cosmic violence. Sometimes the most devastating transformations aren't the loudest. The sun's expansion will erase worlds not with a bang, but with the inexorable creep of heat and radiation, a reminder that in the universe destruction wears many faces. By the time the red giant era ends, the solar system we know will be gone forever. The asteroids will have been baked dry, the gas giants' moons melted into temporary oceans, and Earth, if it still exists at all, reduced to a blackened rock orbiting a ghost star. Yet this very process will enrich interstellar space with carbon, nitrogen, and other life-essential elements, potentially seeding future generations of stars and planets. The sun's death, like all cosmic violence, isn't just an ending, it's part of an endless cycle where destruction and creation are forever intertwined. Beyond the orbits of Neptune and Pluto lies a frozen graveyard of primordial debris, the Oort cloud, a spherical shell of icy bodies stretching nearly a light-year into the void. This distant reservoir holds trillions of comets, leftovers from the solar system's birth, orbiting in such profound darkness that even our most powerful telescopes struggle to detect them. But don't let their invisibility fool you. These ancient icebergs are cosmic loose cannons, and when one gets knocked inward by a passing star or galactic tide, it becomes a long-period comet, a potential planet killer streaking toward the inner solar system at speeds that defy comprehension. The Chelyabinsk meteor of 2013 was a chilling teaser of this hidden threat. That 20-meter space rock, barely the size of a school bus, exploded over Russia with the force of 30 Hiroshima bombs, shattering windows across 200 square miles and injuring over 1,500 people. Yet compared to an Oort cloud comet, Chelyabinsk was a firecracker. Long-period comets like Hale-Bopp or Hyakutake can be dozens of kilometers wide, carrying enough kinetic energy to dwarf all the nuclear weapons ever built combined. And unlike near-Earth asteroids, which often give us years or decades of warning through repeated orbits, These icy intruders can appear from the depths of space with just months or even weeks to spare. What makes Oort cloud objects so treacherous is their unpredictability. Their orbits stretch so far that a tiny nudge from a galactic tide, a rogue star brushing past the solar system, or even the gravitational whisper of the Milky Way itself can send them plummeting sunward like a boulder dislodged from a cliff. By the time we spot one, it might already be too late to deflect. Take comet Neowise in 2020, discovered just 4 months before its closest approach, or the infamous comet Magnetars in 2007, which swung around the Sun with a tail so bright it was visible in daylight. Had either been on a collision course, humanity would have had virtually no time to react. The real terror lies in the math. Statistically, a civilization like ours should expect a civilization-ending comet impact every few 100,000 years. The last one likely struck 13,000 years ago, possibly triggering the Younger Dryas cooling event that wiped out mammoths and early human cultures. And because Oort cloud comets spend most of their time in the deep freeze, their ices remain pristine, meaning they don't develop the telltale tales that make comets easier to spot until they're already too close for comfort. Yet for all their danger, these icy wanderers also carry secrets about our origins. Locked within them are unchanged samples of the solar system's building blocks, clues to how Earth got its water and organic molecules. Missions like the European Space Agency's Comet Interceptor aim to study one up close, but the irony is stark. The same bodies that might have delivered life's ingredients could also snuff it out in an instant. So while the Oort cloud remains a frozen enigma, its occasional messengers serve as a humbling reminder. The universe doesn't care about our calendars, our telescopes, or our best-laid plans. Somewhere in that dark shell, the next planet-altering comet might already be stirring, its trajectory set on a course we can't yet see. The Milky Way is far from alone in its cosmic journey. It's part of a slow-motion collision course with the monstrous Virgo cluster, a gathering of over 1,000 galaxies some 54 million light-years away. This isn't just a future meeting, it's an inevitable demolition derby on a scale that defies human comprehension. Right now, our local group of galaxies, including Andromeda and the Milky Way, is racing toward Virgo at nearly 2 million miles per hour, pulled by gravitational forces we can't escape. When we finally arrive in about 7 billion years, the chaos that unfolds will make our upcoming merger with Andromeda look like a gentle fender bender. What makes Virgo so dangerous isn't just its size, it's the environment. The cluster is filled with superheated gas reaching millions of degrees, a plasma soup that acts like cosmic sandpaper against incoming galaxies. As the Milky Way plunges into this inferno, the friction will strip away our precious reservoirs of star-forming gas, leaving our spiral arms ragged and starved. Without fresh gas to birth new stars, our galaxy will gradually fade from a vibrant spiral into a dull, lifeless elliptical, a cosmic zombie, bloated with aging stars but incapable of creating new ones. But the real fireworks will happen at the center. The supermassive black hole lurking in the Milky Way's core, currently quiet and well-fed, will suddenly find itself swarmed with torrents of gas ripped from our galaxy's body. Like a beast waking from hibernation, it will gorge on this unexpected feast, transforming into a blazing quasar that outshines every star in the galaxy combined. The same fate awaits Andromeda's black hole. Both will erupt in tandem, their jets carving through neighboring galaxies like cosmic blowtorches. For a brief, spectacular period, our merged galaxies will become the brightest objects in the local universe, visible from billions of light-years away. Yet the violence doesn't stop there. The sheer gravitational turbulence of the Virgo cluster will wrench stars from their orbits, flinging them into intergalactic space like sparks from a grinding wheel. Some estimates suggest up to half our stars could be lost this way, condemned to drift forever in the freezing void between galaxies. Others will be captured by larger neighbors, becoming stolen citizens of foreign worlds. Our familiar constellations will scatter beyond recognition, the night sky rewritten by forces beyond comprehension. The eerie part, this isn't speculation, we're watching it happen elsewhere. Telescopes have caught galaxies in the act of being dismantled by clusters, their gas tails streaming behind them like cosmic battle scars. The spiral galaxy M87, already at Virgo's heart, shows what awaits us: a giant elliptical surrounded by thousands of globular clusters, the remnants of galaxies it's already consumed. The universe doesn't just create, it recycles, and our turn in the shredder is already written into the fabric of space-time. So while 7 billion years might seem comfortably distant, it's a blink in cosmic terms. The Milky Way as we know it, with its spiral arms, star nurseries, and familiar neighbors, is already living on borrowed time. Every galaxy, no matter how grand, eventually meets the same fate, torn apart, repurposed, and reborn as part of something larger. Our merger with Virgo won't just change the Milky Way, it will erase it, proving once again that in the universe's grand story, even galaxies are just temporary arrangements. On August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a 72-second burst of radio waves so intense that astronomer Jerry Amon scrawled, "Wow." In red ink on the printout, this signal, emanating from the constellation Sagittarius, remains one of the universe's most tantalizing enigmas. It blasted at a frequency of 1,420 MHz, precisely the range scientists predicted an alien civilization might use to broadcast its existence. The signal's intensity spiked and faded exactly as expected. If it originated from deep space, a fingerprint that set it apart from terrestrial interference or satellite noise. For decades, the WOW signal stood as the best candidate humanity had ever found for extraterrestrial contact until an unexpected twist emerged. In 2017, researcher Antonio Paris proposed a counterintuitive explanation: comets. Specifically, two previously undiscovered comets passing through the same patch of sky might have reflected sunlight off their hydrogen clouds, mimicking an artificial transmission. While this theory seems to solve the puzzle, it left many astronomers unconvinced. Comets don't typically emit such focused, narrowband radio bursts, nor do they explain why the signal never repeated despite years of follow-up observations. The truth is, even if the WOW signal wasn't aliens, its sheer peculiarity makes it a testament to how little we understand about the universe's more bizarre emissions. Cosmic radio bursts like this one aren't just rare, they're often one of a kind. Fast radio bursts, for example, erupt with the energy of 500 million suns in mere milliseconds, yet their origins remain hotly debated. Some might come from supermagnified neutron stars, others from cataclysmic collisions, but no single explanation fits every case. The WOW signal falls into this same category, an outlier that defies easy classification. It's a reminder that the cosmos is packed with phenomena we've yet to witness twice, let alone comprehend. What makes the WOW signal so haunting isn't just its mystery, it's the timing. It appeared during humanity's brief technological window, a flicker of radio awareness amidst eons of cosmic silence. Had it arrived a century earlier, we wouldn't have had the tools to detect it. A century later, and Earth's radio noise might drown it out entirely. That fleeting intersection of capability and chance makes it unique, a whisper from the void that arrived precisely when we were listening. Whether alien or natural, the signal's legacy endures. It taught us that the universe is stranger than we imagined, capable of producing signals that straddle the line between natural wonder and deliberate message. And while we may never know its true origin, the WOW signal remains a humbling lesson. In a cosmos this vast and violent, even the most mundane explanations often lead to deeper questions. Somewhere out there, another signal might be waiting, one will only recognize if we keep listening. Hidden deep in the cosmic shadows, roughly 220 million light-years from Earth, lurks one of the most baffling gravitational mysteries in the universe, the Great Attractor. Picture an invisible hand tugging at the fabric of spacetime itself, pulling entire galaxies, including our own Milky Way, toward it at speeds exceeding 1,000,000 miles per hour. This relentless force defies easy explanation, bending the paths of thousands of galaxies into a slow-motion river of stars flowing toward a point in the constellation Centaurus. What could possibly wield such power? For decades, the Great Attractor remained obscured by the Milky Way's own galactic plane, a thick band of dust and stars that blocked our view like a cosmic blindfold. But thanks to infrared and radio telescopes piercing through the interference, we've glimpsed the heart of this anomaly, a staggering concentration of mass, likely a supercluster of galaxies so dense it bends the surrounding universe to its will. The Norma cluster sits at its core, a sprawling metropolis of galaxies bound together by gravity, but even this colossal structure can't fully account for the attractor's pull. There's something more lurking in the darkness, something we still don't fully understand. One terrifying possibility: the Great Attractor might just be the tip of the iceberg. Beyond it lies an even more massive structure dubbed the Shapley supercluster, a gravitational titan containing tens of thousands of galaxies. Together, these regions form part of a vast cosmic web, where galaxies align along invisible filaments like beads on a string, drawn together by the universe's largest and most mysterious forces. Some theorists speculate that dark flow, a mysterious, large-scale motion of galaxy clusters, could hint at structures so enormous they dwarf even the Great Attractor, stretching beyond the observable universe's edge. Yet the true nature of this gravitational enigma might be even stranger. Alternative explanations range from exotic physics, like flaws in our understanding of gravity itself, to the influence of parallel universes exerting unseen forces on our own. Whatever the answer, the Great Attractor forces us to confront a humbling truth. The visible universe we study is just a fraction of what's actually out there. The real architects of cosmic motion might be lurking in the darkness, invisible and unknown, shaping the fate of everything we can see. So while the Milky Way's march toward this mystery is slow, we won't arrive for tens of billions of years. Its existence reminds us that the universe is far weirder than we ever imagined. Behind the serene beauty of the night sky, there's a hidden symphony of forces at work, and we're only beginning to hear its faintest notes. The Great Attractor isn't just pulling galaxies, it's pulling back the curtain on the universe's best-kept secrets. The Boötes Void is the universe's ultimate ghost town, a sprawling cosmic desert so vast it could swallow thousands of galaxies whole without leaving a trace. Stretching 330 million light-years across, this eerie emptiness contains barely 60 galaxies where there should be thousands, making it one of the largest known voids in existence. If the Milky Way sat at its center, we wouldn't have discovered other galaxies until the 1960s, their light only just reaching us across the unimaginable gulf. This isn't just a quiet corner of space, it's a gaping hole in the cosmic web, a place where the universe forgot to arrange the furniture. How does something this empty even exist? One of the most mind-bending theories suggests the Boötes Void might be a scar from the early universe, a collision between two bubble universes during cosmic inflation. Picture this: in the first fraction of a second after the Big Bang, space-time expanded at breakneck speeds, creating bubbles of reality like foam in a sink. If two of these bubbles brushed against each other, their collision could have carved out a void, leaving behind a sterile no-man's land where matter was literally pushed aside. It's like shaking a box of glitter and finding a perfect, empty circle where none stuck, a flaw in the fabric of creation itself. But there's another, equally unsettling possibility. The void isn't empty at all. Instead, it might be filled with dark energy, the mysterious force accelerating the universe's expansion. If dark energy clustered here in higher concentrations, it could have repelled galaxies like oil pushing away water, creating this bizarre desert. Some astronomers even speculate that the void's gravitational weirdness distorts our observations, making it appear emptier than it truly is, a cosmic mirage hiding secrets we can't yet see. What makes the Boötes void so haunting isn't just its size, it's the silence. Most cosmic voids are part of the universe's natural structure, the gaps between galaxy clusters where matter is thin but not absent. This one defies the rules, challenging our understanding of how the cosmos organizes itself. If voids like this are more common than we thought, they could rewrite the laws of cosmology, forcing us to rethink how matter spread after the Big Bang. Yet even in this emptiness, there are whispers of resilience. The few galaxies stranded in the void, like isolated islands in an endless ocean, have adapted to their lonely existence. Many glow with the blue light of young stars, suggesting they're burning through their gas reserves in a desperate race against the void's hunger. Others might be surrounded by dark matter halos massive enough to cling to their gas against all odds, tiny oases in a desert of nothingness. The Boötes void is more than a curiosity, it's a cosmic puzzle box, one that might hold clues to the universe's most profound mysteries. Whether it's a collision scar, a dark energy anomaly, or something even stranger, this vast emptiness reminds us that the universe is full of surprises. And somewhere in its darkness, there might be answers waiting, not in the light of galaxies, but in the spaces between them. Imagine a single collision in space, two satellites smashing together at over 20,000 miles per hour. Now picture that impact spawning thousands of fragments, each traveling just as fast, each capable of triggering another collision. That's the nightmare scenario of Kessler syndrome, a man-made disaster where low Earth orbit becomes so clogged with debris that cascading collisions render entire orbital highways unusable. Unlike natural cosmic hazards like asteroid belts or galactic debris fields, this threat comes from our own technology turning against us, creating a self-sustaining chain reaction that could lock humanity out of space for generations. The comparison to natural cosmic debris is chilling. Asteroid belts may seem chaotic, but their orbits are stabilized by gravity over billions of years, forming predictable patterns. Even the wreckage from galactic collisions spreads thinly across vast distances, but human-made space junk, it's concentrated in narrow orbital bands, packed so densely that a single collision between a defunct satellite and a discarded rocket stage could spawn enough shrapnel to threaten functioning spacecraft worldwide. In 2009, this nightmare became briefly real when Cosmos 2251 slammed into Iridium-33, creating over 2,000 trackable fragments and countless smaller, invisible ones. The math is terrifying, with over 130 million pieces of debris larger than a millimeter now whizzing around Earth. Even tiny paint fleets can strike with the force of bullets. The International Space Station regularly maneuvers to avoid known hazards, but as the debris cloud grows, so does the risk. Simulations show that once a critical density is reached, collisions will spawn more debris faster than it can decay into the atmosphere, triggering an unstoppable domino effect. Suddenly, vital orbits home to GPS satellites, weather monitors, and communication networks become kill zones. Yet the greatest irony lies in what this could cost us astronomically. A cascading debris field would not only endanger future missions but could trap valuable assets like the Hubble Space Telescope in a prison of shrapnel, cutting us off from the cosmos we're so desperate to explore. Some proposals to mitigate this: lasers to nudge debris, nets to capture it feel like bandages on a hemorrhage. Meanwhile, mega-constellations like SpaceX's Starlink add tens of thousands more satellites to the mix, turning low Earth orbit into a high-stakes game of dodgeball. Unlike natural cosmic violence, which follows the indifferent laws of physics, Kessler syndrome is entirely preventable, but only if humanity acts before the first unstoppable chain reaction begins. The clock is ticking, and every piece of debris we add brings us closer to a silent catastrophe where the final frontier slams its doors shut, not with a cosmic explosion, but with the slow, grinding inevitability of our own neglect. The Drake equation, that famous formula estimating the number of intelligent civilizations in our galaxy, has always been a hopeful exercise, a way to quantify our cosmic loneliness. But what if we've been missing the universe's fine print? Hidden in those variables are violent forces that don't just lower the odds, they reshape the entire equation. Gamma-ray bursts, hypernovas, and rogue asteroids aren't just rare disasters. They're systematic filters, cosmic grim reapers that might cull intelligent life faster than it can evolve. Take gamma-ray bursts first. These death beams could sterilize entire swaths of the galaxy, wiping out complex life on any planet unlucky enough to lie in their path. Statistically, Earth should have been hit multiple times in its history, and evidence suggests it has. Tree rings from the 8th century show a radioactive carbon spike, likely from a gamma-ray burst or solar flare. Had it been closer, it wouldn't just have burned our ozone layer, it might have boiled the oceans. Factor this into the Drake equation, and suddenly the L term, the average lifespan of a civilization, shrinks dramatically. A galaxy where gamma-ray bursts sweep through like clockwork could be a gallery of dead worlds, their civilizations erased before they ever built radio telescopes. Supernovas add another layer of chaos. A nearby stellar explosion wouldn't just light up the sky, it would bathe Earth in enough radiation to trigger mass extinctions. Astronomers suspect one might have contributed to the Ordovician die-off 450 million years ago, wiping out 85% of marine species. The Milky Way hosts multiple supernova candidates like Betelgeuse, a ticking time bomb just 640 light-years away. If intelligence requires stable environments over millions of years, supernovas are the ultimate reset buttons, punching holes in the evolutionary timeline. Then there's the asteroid factor. Chicxulub proved even a 6-mile rock can rewrite the rules of life. But smaller impacts are far more frequent. The Tunguska event in 1908, a mere 40-meter asteroid, flattened 800 square miles of forest. Had it hit a city, the death toll would have been apocalyptic. Now scale this up. In a galaxy teeming with Oort clouds and asteroid belts, how many budding civilizations get crushed before they even leave their planet? Recalculating the Drake equation with these variables paints a stark picture. Suddenly, the universe isn't just vast, it's a gauntlet where life must dodge extinction-level events like a sprinter weaving through landmines. The Great Filter might not be a single hurdle but a series of them, each deadlier than the last, yet there's a strange silver lining. If we're here, it means our ancestors survived every cosmic bullet so far. That alone makes us statistical miracles, or proof that life, against all odds, finds a way. The Hubble tension isn't just a scientific disagreement, it's a full-blown cosmic mutiny where the universe's own measurements refuse to agree with each other. On one side, we have the Hubble constant, the rate at which the cosmos expands, calculated by studying nearby galaxies and the flickers of dying stars. These observations give us a clear, precise number. On the other side, we have the afterglow of the Big Bang itself, the cosmic microwave background, which predicts a slightly slower expansion rate. The difference might sound small, but in the precise world of cosmology, it's a gaping chasm, one that suggests we're missing something fundamental about how reality works. What makes this conflict so explosive is the stakes. If both measurements are correct, then our understanding of physics is incomplete. Dark energy, that mysterious force accelerating the universe's expansion, might not be constant after all. It could be evolving, growing stronger or weaker over time. Alternatively, there might be undiscovered particles, a fifth fundamental force, or even flaws in Einstein's theory of gravity itself. Each possibility rewrites the rules we thought govern the cosmos, turning a minor discrepancy into a potential revolution. The tension has only grown sharper with time. In 2019, the Hubble Space Telescope delivered its most precise measurement yet, tightening the error bars so much that the disagreement became impossible to ignore. Some researchers have scrambled for conventional explanations, maybe hidden errors in our measurements or unaccounted dust in distant galaxies. But the more we refine our tools, the more the gap persists, as if the universe is deliberately taunting us with its secrets. One particularly tantalizing theory involves early dark energy, a phantom force that might have surged in the universe's infancy, altering its expansion just enough to leave behind this lingering inconsistency. If true, it would mean the cosmos underwent a violent, unseen acceleration before settling into its current rhythm. Another idea suggests that dark matter interacts with itself in ways we've never detected, subtly warping the cosmic landscape. The Hubble tension isn't just a puzzle, it's a battleground between two visions of the universe. Resolving it could unveil new layers of reality or force us to tear up the textbooks and start anew. Every new telescope, from the James Webb to upcoming observatories like the Vera Rubin, joins the fight, hunting for clues in the light of ancient galaxies or the whispers of gravitational waves. Until then, the universe keeps expanding not just in space but in mystery. Among all the violent cosmic phenomena we've explored, none unsettles our understanding of reality quite like the Boltzmann brain, a thought experiment so bizarre it borders on existential horror. Picture this, in the chaos of quantum foam, where particles flicker in and out of existence at the smallest scales, a freak fluctuation might randomly assemble a fully formed, self-aware brain, complete with artificial memories of an entire life that never actually happened. This isn't science fiction, it's a chilling consequence of thermodynamics and infinity. Given enough time, and in an eternal universe, time is infinite, even the most improbable events become inevitable. The violence behind this concept lurks in the fabric of reality itself. Quantum foam, the seething turbulence of space-time at subatomic scales, is anything but peaceful. Virtual particles erupt and annihilate in a frenzy, driven by the raw energy of the vacuum. Occasionally, these fluctuations might stitch together something far more complex than a fleeting particle, an organized structure like a brain conjured from pure chaos. The odds are astronomically low, but over infinite time and space, even a 1 in a Googleplex chance eventually tips in favor of the absurd. What makes this idea so unsettling is its implication. If random fluctuations can spawn conscious observers, how can we trust our own memories or perceptions? The universe might be teeming with Boltzmann brains, brief flickers of awareness doomed to dissolve back into the void, while real beings like us could be statistical impossibilities. Some versions of the thought experiment suggest it's vastly more likely for a single brain to fluctuate into existence than for an entire, orderly universe to evolve naturally. This twists the arrow of time backward, making entropy itself a creator rather than just a destroyer. Tie this to cosmic violence and the parallels are striking. Just as gamma-ray bursts and hypernovas reshape the universe through brute force, quantum fluctuations rewrite reality at the smallest scales. The same primal energies that forged galaxies might also spawn phantom minds, ephemeral witnesses to a cosmos that never truly existed. Even black holes, those devourers of information, find an eerie counterpart in Boltzmann brains. Both erase the line between what's real and what's random. Yet there's a strange beauty in this madness. If self-aware structures can emerge from chaos, then consciousness might be more fundamental than we imagined, a spark that can ignite anywhere, anytime, given the right conditions. The universe doesn't need planets or stars to produce observers. It might do so accidentally in the dark between the ticks of time. So while the Boltzmann brain remains a philosophical nightmare, it's also a testament to the universe's boundless creativity. Even in its most violent, disordered corners, reality keeps surprising us, proving that the line between profound insight and cosmic horror is thinner than we dare admit. From hypergiant stars detonating in supernovas to rogue black holes drifting unseen through the cosmos, the past 30 facts have revealed a universe that thrives on chaos. Gamma-ray bursts capable of sterilizing planets, quasars brighter than 1,000 galaxies, and neutron star collisions that forge gold in their explosive embrace. Each event proves that destruction and creation are two sides of the same cosmic coin. Even Earth hasn't been spared, from the dinosaur-killing asteroid to near misses with solar storms that could have wiped out modern civilization. Yet without these cataclysms, we wouldn't exist. The gold in your jewelry, the oxygen in your lungs, even the atoms in your body were forged in the heart of dying stars. This duality is the universe's greatest paradox. Its violence seeds the very ingredients for life while threatening to erase it in an instant. The same black holes that rip stars apart also anchor galaxies together. The supernovas that scorch worlds also scatter the elements needed to build new ones. Even the sun's eventual death as a red giant, though it will consume Earth, will enrich the cosmos with materials for future planets. Destruction isn't just an end, it's the universe's way of reinventing itself. So the next time you gaze at the night sky, remember, those tranquil stars are anything but peaceful. Beyond the stillness, titanic forces are colliding, exploding, and reshaping reality itself. The cosmos is a battlefield, a forge, and a canvas all at once. And we're here against all odds to witness it. If these violent wonders left you in awe, smash that like button and share this video with fellow space enthusiasts. Let's keep unraveling the universe's darkest, most dazzling secrets together. After all, the cosmos never sleeps, so why should we look up? The next cosmic spectacle could be unfolding right now.